So this is part 1, number 14.
Yeah.
So you have to use the Chinese remainder theorem.
Yes, I use also the.
So if we have x congruent to 2 mod 5 and x congruent to 3 mod 7, this is solvable if 2 is congruent to 3 modulo the greatest common divisor of 5 and 7, which is 1. So this is okay. There will be a solution. And to find it, you can say, well, x is congruent to 2 mod 5 means x is a number, any number of the form 2 plus 5 times y. That's what it means to say that x is congruent to 2 mod 5. On the other hand, or in addition, x has to be congruent to 3 mod 7. So we need to find a y such this is congruent to 3 mod 7, which is the same as 5y congruent to 3 minus 2 or 1 mod 7. So we have to find a solution of this. So can you find a solution of this linear congruence?
The one you just wrote.
Yes.
Let me see. X equal to 2.
Well, you're looking for y, not x.
For y, I know. Let me see. I have like to do a lot of calculation.
So you just start different numbering. Try y equals 0, 1, 2, 3, 4, 5, 6. And as soon as you find the solution, there's only one solution, and that's it.
Okay, let me see. Okay, 1, 8, 15. Can we try like x? Let's see.
Well, does y equal 0 work?
I'm trying to do something simple here, like to see if I can get it like directly.
Well, the simplest thing is just to experiment. Just try the numbers in order.
Okay, I think if for y equal to 3, it should be fine.
Okay.
Y equal to 3 will be 15 minus 1, 14 divided by 7.
Okay, so this is the same as y congruent to 3 mod 7.
Yeah.
Right? So y is a number of the form, any number 3 plus 7 times z. And x, which is 2 plus 5y, that's 2 plus 5, and y is 3 plus 7z. So that's 2 plus 15 plus 35z.
Excuse me, where did you get the x equal to 2 plus 5y?
That's how we started. Right? The first congruence.
Okay.
Right? So this is 17 plus 35z. So the solution is any number congruent to 17 modulo 35. So there are infinitely many solutions, but they all satisfy one congruence. And you can check. 17 minus 2 is 15, is divisible by 5. And 17 minus 3 is 14, is divisible by 7. So this is the solution.
Wait. 2 plus 15. 17. It's kind of confused. Oh, I see now. But for this part, I think they was asking like for a multiple solution, right?
Yeah, find all integer solutions. So all integer solutions of this set of congruences is all integers x congruent to 17 mod 35. So x is one of the numbers 17. 17 plus 35 is 52. 87 minus 18, and so on. I mean, there's infinitely many numbers, but they all satisfy this congruence.
Okay.
Right? So that's part A.
Oh, this is the final solution, right?
This is the solution.
Okay. Okay.
And for part B, you have x congruent to 2 mod 15 and x congruent to 3 mod 21. And there's a solution if and only if 2 is congruent to 3 modulo the greatest common divisor of 15 and 21.
Oh,
which
the
is
one I was just like asking you like to do was and the A because I did the A. I thought like the one you were like doing is the B. I was asking for the B.
Oh, this is the B, and this congruence is not true, so no solution.
Yeah, that was the reason because I was trying like to find and
Well, all solutions are the empty set. There are no solutions.
and how sorry. So when you find like the GCD of 15 and 21, that's supposed to be 3, right?
It is 3, yes.
So you mean like you cannot find like any X that can give us like this solution?
Correct. Absolutely correct.
Can we just it's like kind of confused. Okay, let me see something here. 2, 3, 4. And how did you know that?
That's the Chinese remainder theorem. So I'll remind you what the Chinese remainder theorem says. If you have x congruent to A mod M, x congruent to B mod N, so this has a solution if and only if A is congruent to B modulo the greatest common divisor of M and N. Right. And if, so if this condition is satisfied, then the set of all solutions is a unique congruence class modulo the least common multiple of M and N. So when M is 5 and N was 7, the least common multiple was 35. And that's why the solution for part A was one congruence class modulo 35.
Okay.
And Professor, which what was that for? Was that for one of the proofs?
This was, no, this was just a calculation. This was in the part 1, problem number 14.
Oh, okay, okay. Because I want to know if you could go over the I guess theorem 1 and 2 again of the review part 1.
Okay. So it really is extremely simple. It's just the definition. You just have to know the definitions. So, what is the definition of an abelian group? Of an additive abelian group?
Yeah, I forgot.
So first of all, so you need a binary operation of addition. So
Professor,
yes.
this for the abelian group, it's supposed to be 4 properties, right?
It's supposed to be what?
To solve this one, we suppose like to go into 4 different steps, like closer.
Yeah. So that's what I'm doing. So you have an operation of addition in the group, and the addition has to be associative. There's an additive identity. That means an element where x is 0, where x plus 0 and 0 plus x equals x for all x. Associative means x plus y plus z is x plus y plus z. There has to be an additive inverse. So given x, there is a y such that x plus y and y plus x equals 0. And addition has to be commutative. X plus y equals y plus x for all x and y. So addition in the integers satisfies these properties. I mean, you know from elementary school, the integers satisfy these properties. So we're done. That's all there is. You have to say, addition satisfies the associative law. The number 0 is the additive identity. If you have a number x, the number minus x is the additive inverse. And x plus y equals y plus x for all x and y. So that's the proof of that theorem.
Thank you, Professor.
Right. And then to show that the integers form a commutative ring, you have to know, well, what is a commutative ring? So R, a set R with addition and multiplication, so 2 binary operations, is a commutative ring. If it satisfies the following. First, under addition, R is an additive abelian group. Second, or next, multiplication is associative. That means for any 3 elements, x, y, and z, xy times z is x times yz. And there is a multiplicative identity. Let's just call it 1, where x times 1 and 1 times x is equal to x for all x. And then you have the distributive law, which is x times y plus z is xy plus xz, and y, or y plus z times x is yx plus yz. But let me write this carefully. So y plus z times x is yx plus zx. So if addition and multiplication satisfy these properties, you have a ring. And if multiplication is commutative, that means xy equals yx, then you have a commutative ring. And you know that the integers satisfy these properties, so the integers form a ring. Okay?
Yes,
Any
thank you,
questions?
Professor.
Yep.
Professor, could you also possibly go over 7 in part 1, the mathematical induction question?
Sure.
Cool.
So we want to prove by induction that if you take the sum of the first n cubes, that's like taking the sum of just the first n integers and squaring the sum. So what you have to know, of course, so must recall, we proved this by induction, that if you take the sum of the first n integers, that's 1 plus 2 plus 3, n minus 1 plus n, this is equal to n times n plus 1 over 2. So you can prove this by induction, for example. So you have to know this. So we want to prove this statement by induction. What does it say for n equal 1? Summation k goes from 1 to 1 of k cubed, that's just 1 cubed, which is 1. And summation k goes from 1 to 1 of k squared, this is just 1 squared, which is 1, and they're equal. So it's true for n equal 1. That is, this statement, what we have to prove, is true for n equal 1. What about, let's just do another case. Suppose we take n equal 2. You take summation k goes from 1 to 2k cubed. This is 1 cubed plus 2 cubed, which is 1 plus 8, which is 9. And if you take summation k goes from 1 to 2k cubed, this is 1 plus 2 cubed, sorry, squared, which is 3 squared, which is also 9. So it's true for n equal 2. Let's do another example just to convince ourselves that this is correct. Suppose we take the sum from 1 to 3 of k cubed. That's 1 cubed plus 2 cubed plus 3 cubed. That's 1 plus 8 plus 27. That's 36. What's the sum from 1 to k, from 1 to 3 of k? That's 1 plus 2 plus 3, which is 6. If you take the square of that, you get 36. Right? Still the same. So we know this statement is true for n equal 1, n equal 2, and n equal 3. So how do we prove this by induction? So that n be greater than or equal to 1, and assume it's true, the statement is true for n. So if you take, so then you must prove for n plus 1. So we take the sum from k equal n plus 1 of k cubed. So what is that? That's the sum of all the cubes from 1 to n plus 1. That's the sum of all the cubes up to n plus the last cube, n plus 1 cubed. And by the induction hypothesis, this is equal to the sum from 1 to n of k squared plus n plus 1 cubed. And this, the sum of the first n integers, is n times n plus 1 over 2, and we're squaring that, plus n plus 1 cubed. So now we just do some high school algebra. You can factor an n plus 1 squared out of both of these terms. If you take n plus 1 squared out of the first term, we have n over 2 squared. And if you take n plus 1 squared out of the second term, you're left with just n plus 1. Okay? So, all right, so any questions about this? The sum of the first n plus 1 cubes is the sum of the first n cubes plus the n plus first cube. And by the induction hypothesis, this equals this, equals this. And then I just factor out this n plus 1 squared. So this is n plus 1 squared. This is n squared over 4 plus n plus 1, which I can put over a common denominator. It's 4 times this over 4. So this is n plus 1 squared, factor out the 4. And what I have here is n squared plus 4n plus 4. And then you have to recognize that this is just n plus 2 squared. So what I have is n plus 1 squared, n plus 2 squared over 4, which is 2 squared, which is n plus 1 times n plus 2 over 2, all squared. But this is just the formula for, in the square brackets, the sum of the first n plus 1 integers squared. And that's the end of the proof. That's what I wanted to prove. Any questions about this?
No, that was good. Thank you, Professor. And someone's asking for some questions in the chat, I believe.
Right. Okay. No, but I just want to make sure this is okay before I go on.
Oh yeah, I understood it. Thank you, Professor. Appreciate it.
No one else has a question? Okay. So someone asked about 2 problems about matrices, number 4 and 5. So review to say number 4. So we're looking at the set of all matrices of the form A 2b, 3c, and d, where a, b, c, and d are integers, and the determinant ad minus, because 2b times 3c is 6bd, 6bc is 1. So our matrices of integer matrices with determinant 1, where this coordinate is even and this coordinate is divisible by 3. And we want to show it forms a group. So first of all, we want to show that G is closed under matrix multiplication. That is, if we have two matrices of the form of this form, then the products of this form. So suppose we have A, 2B, 3C, and D, and another matrix of that form, E, say 2F, 3G, and H. Okay? So these are two integer matrices with the upper right coordinate divisible by 2 and the lower left coordinate divisible by 3. So when we multiply it, we get AE plus 6BG, 2AF plus 2BH, 3CE plus 3DG, and 6FC plus DH. Okay, so matrix multiplication, this is what you get. And if you look at for this second, I have my first coordinate, that's an integer. My second coordinate, this is 2 times AF plus BH. This coordinate is 3 times CE plus DG, and this coordinate is 6FC plus DH. So when I see that when I multiply two elements of this set, I get a matrix where this coordinate is even and this coordinate is divisible by 3. And how do I know? And how do I know that the determinant is 1? This times this minus this, right? So, but the determinant is 1 because the determinant is multiplicative. That is, if we call this matrix X and this matrix Y, this is the product X times Y. The determinant of X, Y, we know is always the determinant of X times the determinant of Y. And if these are in the group, in the set, this is 1 times 1, which is 1. So that proves that this is closed under multiplication. What's the identity? 1, 0, 0, 1. But 0 is the same as 2 times 0, and 0 is the same as 3 times 0. So this matrix also satisfies the conditions to be in the set G. And is it closed under taking inverses? If you take A, 2B, 3C, and D, the inverse we've proved many times is D minus 2B minus 3CA. And again, this is even, this is divisible by 3, so this is in G. So this set of matrices is closed under multiplication, contains the identity, and contains the inverse of each element. So it's a group. Okay. That's what we needed to prove. Okay. So all of these steps have to be checked. So there is some work you have to do, but that's the way it is. Sometimes you have to do some work. So any questions about this? I mean, there are, 3 different things that have to be checked, maybe even more than 3.
Professor,
Yes,
the part you restate that the determinant is 1 because the determinant of the multiplication equals to 1. Do we really have like to say that since it's already said or
well, here I multiply these two matrices and this is what I got. But so it satisfies the condition that this coordinate is divisible by 2 and this coordinate is divisible by 3. But I also need that this times this minus this is 1. How do I know that?
oh, you have to say, okay, I see.
Right. This is part of the definition of G. Let's see, and then are there any other questions about this problem? Okay, and then what about number 5? Number 5, we have some 3 by 3 matrices. So there's some set, that's just some notation for it. But this is 3 by 3 matrices of a very simple sort. Down the diagonal, it's just ones. Below the diagonal are zeros. And here we have A, B, and C. These are just all possible choices of integers. And we want to prove this is a group. So you have to show, first of all, that it's closed under multiplication. So you take two elements of this group, so with A, B, C, and D, E, F, and what do you get when you multiply them? So row into column, you get 1. So let's see, first row, first column, second row, first column, third row, first column, it's 1, 0, 0. What about the second column? First row, second column, I get D plus A, or A plus D. Here I get 0 plus 1 plus 0 is 1, and 0, 0, 0. And then for the third column, I get F plus AE plus C. And here I get F plus E, or is E plus F. And here I get 1. So this is a matrix with ones down the diagonal, zeros underneath the diagonal, and some integers here. So this is another matrix in this set. So this set is closed under multiplication. What about the identity matrix? Well, that's easy. The identity matrix 1, 1, 1 does have ones down the diagonal and zeros below. It happens to have zeros above the diagonal, but that's fine. So this set contains the identity. So maybe the only hard thing is to show that this set contains the inverse of each matrix. So if you have an element in this set, we want to find a matrix that looks like this, where this product is equal to the identity. So this is given, and I want to find X, Y, Z that's such that this is the identity. And now we have the rule for multiplying two matrices. It looks like this. Here we have A plus X. Here we have B plus Y. Here we have C plus Z plus AY. So if you take this matrix times this matrix, this is what you get. And you want to choose X and Y so that this is the identity. So you must have this coordinate is 0, which means x has to equal minus a. You must have b plus y equals 0. So y has to be minus b. And finally, you have to have c plus z plus ay equals 0, which means z is c minus a is minus c minus ay. But y is minus b, and minus a times minus b is ab minus c. So this is what z has to be. So if you have this matrix, the inverse is the matrix where x is minus a, y is minus b, and this coordinate is ab minus c. And again, this is in the set. So you actually, again, you have, this is a hard problem because you have to sort of think about what it is that you need to check, and then you need to check it. And in math and physics, this is actually a very important group.